As you know, the last lecture in Chemistry 103 is traditionally set aside to do a series of demonstrations, hopefully illustrating a number of the concepts and phenomena that we have dealt with this semester. And in order to continue with this tradition and also continue with the safety precautions that we usually have, I'm going to start off by putting on my safety glasses, as all of you usually remind me. Safety, as you know, is extremely important in all the activities that we go through, whether it is in the laboratory or in a fun type lecture like this one. Now, you know, we've talked about properties of gases, we've talked about the properties of liquids, we've talked about a number of concepts, and what I'd like to do today is go through a series of demonstrations to illustrate principles and to discuss concepts that we have seen before. You know that we're all surrounded in this room and everywhere else by air. We breathe air all the time. And so what I'd like to do is show you the effect that the air that we are in exerts in terms of pressure. And what I have here is this can that has been heating for some time. It's got some liquid in it. And you look closely here, you can see that the vapors are escaping. And what I'm going to do is fairly soon stopper this can here so that no more liquid. And what you see is the can is making a lot of noises, and as it cools down, it's beginning to collapse because it's evacuated on the inside, and the pressure outside is greater than the pressure that's inside. In fact, it's kind of assuming this funny shape here. So why don't we just push this back here and let it go for a while. See, the effect of the atmospheric pressure then is quite real if you evacuate the can as we have done here. Now, you know, air is composed of nitrogen, oxygen, and a few other gases. These gases constitute all the composition of air, including, as I say, nitrogen, oxygen, carbon dioxide, some hydrogen, and the various proportions are the ones that you see here. And what I'm going to do in this lecture is talk about the properties of nitrogen in the gaseous phase and in the liquid phase, as well as oxygen in the gaseous phase and in the liquid phase, and talk about the properties of matter that we have, that we know about. Now, carbon dioxide is a component of air, and I would like to do a couple of demonstrations now to show you that it is indeed something that we do breathe. What I have here is a solution of calcium hydroxide, lime water. And what I'd like to do is ask for a couple of volunteers. How about you? Would you come up here, please, and just stand over here, right where I'm standing, and then when I say go, start blowing into the solution, okay? And I'm going to ask you also to come up and stand right next to her, okay? And you turn this way. How about turning that way, okay? Turn this way, and you turn that way, all right? And when I say go, you start blowing. No, don't blow, don't suck, all right? Why don't you hold it this way so other people can see what's going to happen? Okay, ready? Go. Not very hard, not very hard. Just and you see that in one of the containers here, we are developing a rather cloudy situation. And what's happening is that the calcium hydroxide is absorbing the carbon dioxide that they are exhaling, and they're forming calcium hydroxide. And I think it's pretty close to a draw, so why don't you just stop now. Thank you both very much. Oh, what I'd like to do is show you how quickly I can beat both of them by using a chunk of dry ice. As you know, dry ice is solid carbon dioxide. And just put the dry ice in the solution here. And you see very quickly it gets to be cloudy, and the reaction is between carbon dioxide and calcium hydroxide, and gives you the insoluble limestone calcium carbonate. Now, I want you to watch very carefully what's going to happen next, because this is an illustration of the principles of chemical equilibrium that we have encountered. If you look carefully, you'll see that the cloudiness is disappearing. And in fact, the solution is becoming fairly clear. And that's because of a reaction that is taking place due to the presence of the excess carbon dioxide. The insoluble calcium carbonate, in the presence of excess CO2, goes into soluble calcium bicarbonate. And the calcium bicarbonate is a soluble substance, and therefore we have a clear solution. So this is one of the things that we've talked about, how we can shift the position of chemical equilibrium. And before this equilibrium system runs out here, let me just keep it going a little bit here by, again, using the dry ice. The systems that we will look at today, as I mentioned before, deal with the nitrogen and oxygen gases in the liquid state. And so what we're going to do is look at a temperature scale now, just to give us a fix as to what range of temperature we're looking at. And the temperature that we are most familiar with, of course, is the temperature of freezing water and room temperature. And if we look at this scale now, you'll see the range that we are talking about, both in centigrade and Fahrenheit. And as you know, the metric system is upon us, and pretty soon we're going to do away with the Fahrenheit scale and think only in terms of the centigrade scale. Just to give us an idea about the ranges we're talking about here, dry ice, solid carbon dioxide, sublimes at minus 78 degrees centigrade, and liquid oxygen boils at minus 183 degrees. Liquid nitrogen boils at minus 196 degrees centigrade. And so what we're going to do is dive way down to this low temperature region and see what happens to matter in this environment. One thing that we want to show you right away is what this liquid nitrogen that I'm talking about looks like. It's really a liquid, and as you can see, it dances around. In fact, it's a pretty good device for dusting the top of the table here. And so I want to clear the table here, so I'll do that. It's very cold because, as I mentioned before, it is at a temperature of minus 196 degrees centigrade. And one thing that we can do is actually have some coffee. When you have coffee, you've got to boil it, right? So we'll start boiling off some coffee here. We'll use as a heat source this ice bath that we have here. And you see the ice bath is at a warmer temperature than the liquid nitrogen. You can see that the nitrogen is boiling, and we are quite ready to drink our coffee. Actually, there is another effect that I'd like to show you now, which is if I want to help things out a little bit here, I'm just going to heat this a little faster by using this heat source here. And of course, the nitrogen boils off faster. In the process of this reaction taking place, we can make some observations about the changes that are taking place in the system. For one thing, it's getting pretty hot here, so I'm going to take it away from the heat. And if you look at the bottom of this pot, you see some white material there. And as students who've had now a semester of chemistry, I'm fairly confident you can tell me what this material is. Would anyone want to venture? It's a white substance, right? Now just think of what we're doing. We had some cold liquid nitrogen inside the coffee pot, and we supplied it with heat from this burner that has, of course, natural gas as a fuel. So what is this white stuff that's formed at the bottom here? What?
Either CO2 or H2O.
Somebody said it's either CO2 or H2O. Where'd the CO2 come from? It is CO2. Where'd the CO2 come from?
Methane burning.
You sound like a TA. Are you a TA? It's a student. Well, that's very good. The methane, the combustion of methane yields carbon dioxide and water, and because the liquid nitrogen is at such a low temperature, the nitrogen is in the liquid form, then the material that condensed at the bottom is solid carbon dioxide and of course, frozen water, which is ice. And you see, this is a way of making solid carbon dioxide. Actually, it's not a very good way of making solid CO2 because the liquid nitrogen that you have to use is much more expensive than the CO2 that you end up producing. And, well, we've seen the property of one hydrocarbon, one compound that contains carbon and hydrogen. What I'd like to do next is show you the properties of other hydrocarbons how they behave at this low temperature. And what I'm going to do is take some kerosene, which is a hydrocarbon, and pour some into this test tube. And what I'm going to do is let this kerosene freeze. So I'm going to put it in this. Pardon? Okay, somebody will get it to work fairly quickly. I can't do it from here, you know that, right? I'm having enough trouble as it is by myself. Keep running out of this good stuff here. There we go. Okay, we'll let that cool down for a while. And I'm going to use also the same hydrocarbon we had just looked at. That is the methane. And I'm going to liquefy the methane by cooling it down to liquid nitrogen temperatures. And so what I'm going to do is connect this to the gas outlet, turn the gas on, and just let it condense. Let the gas that I'm bubbling through will condense in due time. And as we're doing that, actually what I really want to do, in order to be able to fish it out, you see some gas is already condensed. You see that? So I'm going to get rid of this. Well, I can get rid of it by just letting it sit here. It'll evaporate. And I'm going to put it in this test tube here because this one has a string on it that I can use to fish it out. I'm also going to look at another compound, actually everyone's favorite compound. That's ethyl alcohol. And to do that, I need to use this test tube that I was using before. Just warm it up a little bit here. It's pretty cold. And I'll take the alcohol. You see, it's a very useful compound. It has many uses that I'm sure you're familiar with. It's used as an antifreeze in one form or another. So we'll let this cool for a while now here. Let's see, how are we doing here? Add a little more nitrogen. Make it go. Well, there are so many properties that compounds have, and we're familiar with them. For example, one compound that we're going to be talking about in the second semester is rubber. And here I have a simple rubber ball, and I wanted to make sure that it is a rubber ball, so I'll just throw it out to you and check it out and see. Is it all right? Got it, right? You want to check it on this side here? There you go. Couldn't catch it. Okay. And what I want to do is see what happens to this rubber ball when I put some liquid nitrogen on it. All right. As usual, the nitrogen is boiling off because the temperature is much warmer than the boiling point of nitrogen. And this thing seems as if it wants to float in nitrogen. That's because the rate at which the gas is escaping is relatively high. And it's also pretty cold in there. So maybe I'll use this thing here. Let it go. Let's see what's happening with these two here. Well, not much is happening here, so we ought to help it along a little bit. Okay. Of course, substances change their properties as you change the temperature, and let's see what happens. It's so cold, I've got to. Let's see what happens to it. That's a shattering experience. If you think that was bad, wait till you hear the rest of this. Another thing, let's see, how are we doing here? Well, this is beginning to freeze. This is beginning to freeze. And how are we doing here? We're doing fine. Another a property that we want to look at is one that deals with a compound that we hear a lot about these days, and a compound that is kind of dangerous, but if you control the temperature, it's not so dangerous. That compound is mercury. What I have here, you see, is a mercury hammer. And what I'm going to do is find some liquid nitrogen first. There we go. I'm going to, again, try to freeze the liquid nitrogen, freeze the pieces of rubber that I have in there. Meanwhile, checking on my two goodies here. And you see, this is solid mercury here. And what I'm going to do now is, I think they're frozen. I'm going to take these spikes, you see, and use a mercury hammer to drive them in. Stuff is cold. One more. Of course, the mercury is warming up, and so are the pieces of rubber, so I'll put the mercury back in the acetone dry ice slush here, and we can get rid of it, and let's see what happens to our spikes. Here's one that I didn't put through. I'll just leave it, let it sit there. And as we're waiting for those to warm up a little bit, let's see what has happened to our alcohol here. And you see that what we have is some hard liquor. I told you. Okay, let's see what's happening over here with this kerosene that we've put in here. Let's go over and warm up the outside a little bit by just putting some water on it. And you see what we have is a kerosene candle. Oh, I know what you're thinking. Yeah, that's it. All right, let's see what we can do here with this kerosene candle. Let's see what's going to happen to it. Of course, the kerosene is going to melt, as you can see here. And if one were living in a liquid nitrogen world, then we would use this kind of candle to supply us with light. And as you can imagine, if I let this go a little longer, the kerosene is going to melt, and the whole thing is going to catch on fire, so I'm just going to blow it out now. And you see our rubber spikes here. There you go. Whoops, they're coming out. If I try to drive them in now, of course I can't do that. Okay, we'll get rid of this here and see what's... let's see what's happening with the methane here. You see, we have some liquid methane down there. I guess I'm not quite ready to get it out yet. So what I'll do is light the burner. And I better find my gloves here. Here are my gloves. They're a little awkward to work with, but they are safer in terms of what I'm going to do now. And you see I have this liquid methane. I'm going to warm it up now by just holding it up here. And as it vaporizes, it's going to... Can you see the flame? You see the flame? You can see the jet. Okay, can you see the jet? That's the liquid methane vaporizing coming out through this nozzle. You can see it's boiling away right there and there. What's happening is that it's coming out at such a fast rate that it's putting out the flame. So we'll just let this go for now. Luckily, we didn't have any need for these asbestos gloves, because in the past when I've done this, sometimes the methane boiled over and we had a fire. So we'll let this go now. One other thing we can do with liquid nitrogen, and that is the... well, I'll show you. You take a little liquid nitrogen like so, put it in a test tube, and have a little cannon. Fire one. Ready? Stand by. Let's hit this side, making too much noise. Feeble. Well, it's getting a little too warm in here, so I'm going to take a little, do a little stripping here. And I'm glad you agree. Well, one other thing that we're going to do here is to take this balloon, and it's just an ordinary balloon. Of course, it's filled with a gas, you can tell what the property of the gas is, right? You can say something about the density of this gas. I'm glad you agree. Well, one other thing that we're going to do here is to take this balloon, and it's just an ordinary balloon. Of course, it's filled with a gas. You can tell what the property of the gas is, right? You can say something about the density of this gas just from the fact that it's down here, right? It's got a density that's what? Lighter than air or larger than air? Or equal to air? It's definitely not lighter than air because it's not going up. So let's see what happens to it when we try to cool it a little bit here. And you see the balloon collapses, and it looks like the football I put on the chem tip surveys. Well, I'll just pass it on to you there, okay? And just let it warm up a little bit there. Yeah, you can pass it back if you want. Okay. Okay. That's a pretty expensive balloon, you know. The situation this year on the athletic fields has been quite interesting. In fact, Wisconsin had an excellent football team. The hockey team is doing well. And what I thought I would do is try to salute the athletic teams that we have. And I'd like to ask the laboratory demonstrators, the lecture demonstrators, to come out and help me do this. So would you come out, fellows, please?
Hail to the orange, hail to the blue.
Oh, Bucky. Hey, fellas. Bucky? What do you got here, Bucky? A hockey stick. Oh, I see. Well, Bucky, I really intended for them to salute Wisconsin and not the Illinois colors. The hail to the orange, hail to the blue is Illinois. So fellas, can you redeem yourselves a little bit? Can you help me out a little bit here before Bucky, I said, can you help out a little bit? I'm sorry, Bucky. I don't have anything to do with this. Bucky, maybe we can do other things to try to make up for this. That'd be all right, Bucky. Will you give? You're such a good sport. Anything gonna happen here, fellas? It doesn't look like it. Well, one thing we could do, Bucky, is when I go to the, I wish I could say thank you, fellas. So I think I'll let you go to your rooms now. Hey, look, hey, something did happen. Look at that, Bucky. Sort of. Well, there you go. How's that, Bucky? Right? Right, there you go. Okay. Bucky, I've seen you at the football games. I've seen you at the hockey games. I always go to these games. And one thing that I do is when I go to these games is I just have a lot of pop over there, you see, and what we have here is just a pop bottle, Bucky. Bucky, I'll tell you what, Bucky. Bucky, I'm going to try to make you feel at home, and I'm going to use another gas here. Actually, this pop here turned off my gas over there. So let's use this and see what happens here, Bucky. Is there?
Good evening, hockey fans.
How's that, Bucky? No? Well, I'll tell you what, Bucky. Nothing is working out right for you. We have the wrong colors. The colors don't change on time. What I'm going to do is call for some of my friends to help me out, and they have done this already by actually writing a poem for me. And what I'd like to do is read this poem to you. I'd like to dedicate this to you, Bucky, to try to appease you and to make sure that you are happy with this visit that you've made. So the poem goes something like this. Ready, Bucky? I promise you this will work. Oh. There once was a girl from Nantucket. Oh, Bucky, no, Bucky. Somebody slipped this into my notes. Let me try again, okay, Bucky? You're such a good sport, Bucky. Okay. Once upon a Christmas dreary, in the lab of Shakhashiri. Christmas, you say, and in the lab? Yeah, I have to pay my bar tab. You didn't get that, Bucky, no? You don't like that? Let me go on, Bucky, okay? I helped write this poem. But that's not the part I wrote, okay? You'll get to the part. We'll get to the part that I wrote, okay. Ring stands stood in darker gloom, scattered widely round the room, so thin and spare that none could match the cedars of Lebanon. You know, Bucky, I'm from Lebanon originally, do you know that? No mistletoe there was for kissing, even you, the stars, were missing, when suddenly there was a shock, when suddenly there was a knock. When suddenly there was a knock, Cheery stood in a state of shock. I didn't write this one either, Bucky. Out from the hood jumped Santa Claus, holding 103 books in his paws. Your lecturer enjoyed the glow of the complete combustion of Drago. I wrote this part, Bucky. Santa started to do some flips when he heard about chem tips. Then he shrieked, "From my helper keep abreast. She's not taking your hourly test. Keep your hands off my sweet blonde. I know about your covalent bond." He was being completely unfair. As a Lewis acid, all I wanted was a pair. Santa, while he could, started leaving through the hood. He disappeared with fanfare, and Shakhashiri standing there, So an endpoint in the air. That's it, Bucky. You like that poem, Bucky? You like it, huh? Is it good? Well, I just wanted to try to make up for the kinds of things that went wrong here, and I wanted you to feel at home, with all the chants that you go through at the hockey games and so on, and so. Wow, that wasn't very nice, Bucky, was it? I'll tell you what, Bucky, I've been doing some demonstrations with liquid nitrogen here, and let me do one for you here. Maybe this will make up for all the things that have happened so far. Of course, I need a little more liquid nitrogen here, so I've got it. When you're around, Bucky, we go big, big style. You're not grading me on my technique, Bucky, are you? You are. What I'd like to show you, Bucky, is the effect of. Wow, that wasn't very nice, Bucky, was it? I'll tell you what, Bucky, I've been doing some demonstrations with liquid nitrogen here, and let me do one for you here. Maybe this will make up for all the things that have happened so far. Of course, I need a little more liquid nitrogen here, so I've got it. When you're around, Bucky, we go big, big style. You're not grading me on my technique, Bucky, are you? You are. What I'd like to show you, Bucky, is the effect of liquid nitrogen on different forms of life. And here I have some pretty red roses. And what I'd like to do is show you what happens to the red rose when we put some liquid nitrogen on it. You watching carefully, Bucky? And you see the color remains the same, and it's still a pretty rose. And as you know, Bucky, in the freshman chemistry office, we've had a new secretary this year, and as a token of appreciation for what she's done, I would like to present her with this rose. Is that okay, Bucky? And you know, this illustrious secretary of ours got engaged recently, and so what I'd like to do is present her with this rose. Where is Kay? There's Kay. Here she is. Here you go, Kay. Actually, she really is a marvelous secretary, and I wish you good luck. Now you're engaged, and here's a real rose for you. Bucky, you've been such a good sport yourself. You even deserve a rose yourself. Have a nice holiday season. Good luck on your finals. And yeah? Oh, isn't that sweet? Isn't that sweet? Thank you, Bucky. Thank you. Well, what I'd like to do now is continue with showing you the effect of the cold temperature, the liquid nitrogen on the different forms of life. And what I have here is, as you can see, some grapes. And what we'll do is give them the usual treatment. And they're getting rather stiff. In fact, the whole thing is pretty cold. So let's see what happens if we pour them out. For one thing, they get to be very hard, as you can see here. I'll just throw them to you, and don't eat them now. Don't eat them. They're ready all the way in the back. We see a sky. What's Abdul Jabbar? What's it called? Sky hook. All right. There you go. Here's some more for you over here. Some more for you over here. Well, we can do lots of things with stinks. We can do lots of other things with liquid nitrogen by way of cooking. And for example, we're going to have a 3-minute egg here now. See, this is a honest to goodness egg. We'll put it rather carefully in this beaker here. And we'll give it the usual treatment. All right, we're going to have a 3-minute egg that in a short while here. Whoops, I keep forgetting that stuff is cold. Let this cook like that for a while. Whoops. You think it's ready now? You see, what we have now is a hard-boiled egg. Whoops. It looks to me like the eggs you have in the dorm. Boy. Gosh, we'll try again. Here's another one. Let's try this one again here. And we'll let this one really cook for 3 minutes, okay? That wasn't a 3-minute egg, was it? Yeah, still in there. So we'll let this one go, and as it's cooking, we'll try to look at the effect of liquid nitrogen on other forms of life. And this morning, one of the graduate students here and I went down to the city pond. Actually, Lloyd Williams is his name. He and I went down to the city pond, and here's what we got. Come on, little fella, come on, come on. Come on, come on. Come on, fella, come on. Come on, little fella. And here he is. So what we're going to do is try to cook this little fella. And we'll give him, again, the usual treatment. And as he cooks away, you see liquid boils off. And what's happening to our egg here? You think it's ready now? Huh? 1 more minute. Oh, okay. All right. Let's let that go. How about this fella here? How's he doing? He's doing all right. Oops, it's really... Again, the usual treatment. And as he cooks away, you see liquid boils off. And what's happening to our egg here? You think it's ready now? Huh? 1 more minute. Oh, okay. All right. Let's let that go. How about this fella here? How's he doing? He's doing all right. Oops, it's really... Okay, let's see what's happening with this egg now, all right? For one thing, it's stuck down there. All right, you. And you see it, I heated it too long. It cracked. And that's what happens to the egg when you cook it in liquid nitrogen. And let's see what's happening to this fella here. Let's see what's happening to him here. Well, half of him is cooked anyway, and doggone. I told you, wait till the end, and things will get better. What I'd like to to do now is show you the difference in properties between liquid nitrogen and liquid oxygen. So far, we've talked about liquid nitrogen a great deal, and as you know, liquid oxygen has a boiling point very close to that of liquid nitrogen. For one thing, liquid oxygen is a blue substance, and what I have here is some liquid oxygen. I don't know if you can see that it's blue, but the what I'm going to do is go through a demonstration to show you that the properties of liquid nitrogen and those of liquid oxygen are different. What I have here is a very strong magnet, and if I pour liquid nitrogen in between the two poles of the magnet, you see the nitrogen just runs through and nothing happens to it. But if I take some liquid oxygen and I pour that down, you see what happens to the oxygen being a paramagnetic substance, then is in between the two poles, and there you see the liquid oxygen as it boils away being held between the two poles of this magnet. And as it boils away, then we don't have any oxygen anymore. Just to show you the difference between the nitrogen, let me add some nitrogen here, and you see nothing happens there. Well, liquid oxygen has a number of useful properties. It's used as a fuel, as you know, in rockets, and it's a rocket propellant. But I have a different use for it. Every Wednesday afternoon, after I get done with the lecture here, and after I look at your Chem Tips results, I want to go home and relax. And what I do then is I have usually a cigarette or a cigar, and I have a liquid oxygen cocktail. And that's what I'd like to do right now, because I'm getting a little tired from having all these things go wrong. So I'll just relax for a while, and part of the relaxation, of course, involves having a cocktail, right? And so what I will do is just have a liquid oxygen cocktail. And cheers. Now, the concentration of oxygen here is approximately 700 times the concentration that we have in the air. And you see, one can use this concentration to, when I get done with my cigarette, is just burn off all the ashes like this, and everything goes into the gaseous phase, and there's nothing left over to be picked up. Now, still going away. The season that's coming upon us, as you know, is the holiday season. And I'd like to ask our lecture demonstrators to come out again and salute the holiday season for us. And I'd like to ask Tally to come out and do, well, Mr. Taliaferro.
May I have the phenolphthalein?
Certainly. Let's see, where is it?
I would just like to show you how we produce Christmas colors back in the lab. And we do this by indicators and acids and bases, if we can find them.
Here you are.
Here's, now if I can find something with base in it, where? Oh, there. This is a very dangerous experiment. I'm supposed to have my glasses on while doing it.
Thank you.
In order to be compatible with the rest of the experiment, I have more.
Encore, encore.
I expected that.
Thank you, Tally. I'd like to thank all the people who have helped make this semester a successful semester, and I'd like to thank the people from the Telecommunications Center. I'd like to thank Vince and Bill and Tally and Glenn and Pat and Kay. And most of all, I'd like to thank the students in this course for really making this a most enjoyable semester for me. Happy holidays.